Alright, Physics 2212 Lab 4 circuit. So the purpose of this lab is to predict and observe the behavior of circuits with resistors slash capacitors. We had two circuits which we'll get into, and we also use multimeters to measure the potential difference and current throughout. So assumptions we made in this lab, we did not account for the resistance of the wires and the ammeter, and also we assumed that the online simulation accurately portrays real-world conditions. Our systems for this lab was circuits and surroundings and everything else, and here are our results. First four bullets were from the first circuit, and the second two were from the second circuit. And concepts we used in this lab, we had conservation of energy and charge, we had Ohm's law, V equals IR, Kirchhoff's circuits law, which was the loop and node rule, resistors in series and parallel, how to add them up, time dependence in RC circuits, and we also had linearization, which we used to graph, which you'll see closer to the end. And our circuit models, as stated before, the first one I did in person, second one online, and the first one is right here, which I did in person at the bottom. And we had two 1.5 volt batteries and resistor values, 47 and 100 ohms, and we started out by predicting the I1 and I2 in the top photo, and we got 0.02 amps using Ohm's law. And when we did in real life, we got 19.3 milliamps, which you can see on the bottom, which is close enough. And if we reverse the connection to that ammeter, we get negative 19.3, as you should. Replace one ammeter with a voltmeter, describe the readings. So the voltmeter would read the potential difference across the gap, which would be right around 3, and the ammeter the other ammeter that's not replaced would read 0 because there's an open circuit. And then we measure potential difference at different points of the circuit with only one ammeter. And across A and B it was 2.8 volts, and across C and D it was negative 0.9, and across E and F it was negative 1.9. And if we add all those up, we do get 0, as we should. Seems that our batteries were just a tad low, but that's alright. And we use those values to finish this graph right here. When you attach the voltmeter, why doesn't the ammeter change? The voltmeter has very high resistance, which leads to very little current going through it, so it doesn't affect the ammeter's current reading too much. If we put an ammeter in parallel with a 100 ohm resistor, what happens in the current through the other ammeter? So an ammeter has very low resistance, so nearly all the current flows through it. Instead of the 100 ohm resistor, the other ammeter would read a current close to 0.06 because the overall resistance of the circuit would be 47 ohms. And here's the results. So the resistance of the wire and ammeter and the two resistors that we got by using this potential difference graph. Getting into the second circuit, I did this one online. We have a 9 volt battery, some bulbs, and a 0.2 farad capacitor. This circuit is how I connected the 10 and 20 ohm bulbs. With the 10 ohm bulb connected, the capacitor took about 15 seconds to charge and discharge, and it was 27 seconds for both with the 20 ohm bulb. And with each bulb connected, the capacitor took about with each bulb connected and the capacitor charging, the bulb's light fades out starting from its max, and the current follows a similar trend. Same behavior is exhibited when the capacitor is discharging. Sorry, I'm stumbling a bit. So some observations that we made with our 30 ohm bulb. Right here we connected the 30 ohm bulb, we set the capacitor to discharge, and we graphed the voltage across the capacitor while it was discharging for 20 seconds, and we used these values to make this graph right here. Using the linearization formula, you can see that the slope of this graph is equal to negative 1 over RC. So our experiment RC is 6.36 seconds, and our calculator RC, which is 30 ohms times the 0.2 farads, is 6 seconds. So they're pretty close. Sources of error. Sources of error are limited for the second circuit as it was online, so it should be an ideal model. But it could be that the real world will not follow the conclusions from the virtual experiment for some other limiting factors. And general source of error is rounding errors made in calculations in Excel. And also we had our errors stemming from our assumptions, like how we did not account for the resistance of the wire and the ammeter. So what if and why? Well, just two what ifs. So for the first what if we were doing the lab in real life and used an actual ammeter instead of an ideal one, what is different about the real one and how would it affect the circuit? So a real ammeter has some resistance, and it would cause its current reading in the circuit to be slightly lower. And what if we were doing the lab in real life and use a real battery to charge a real capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor reach full charge, and what would happen in real life? So without any resistor, the capacitor would charge instantly in the ideal model. However, this would not happen in real life as the battery has varying internal resistance that would not allow for this to happen. And that is it for this lab. Thank you.